Many people today are interested in the formalization of mathematics using proof assistance. So I would like to tell you about my experiences formalizing a chapter from a well-known graduate textbook on number theory. I originally gave this talk back in August on the occasion of the retirement of one of my colleagues, Andy Pitts. There are several milestones in the formalization of mathematics that many of my colleagues had been celebrating up to about 2015, so a few years ago. They were the odd order theorem, which is a fundamental resultant group theory, Gödel's incompleteness theorems, done by yours truly, the Kepler conjecture. This was a very big project taking something like 15 years, certifying a proof of a conjecture about the best way of filling space using spheres. This was done using two separate proof assistants. But something happened in 2017. The main thing is an increase in sophistication. So suddenly an interest in simply defining, not proving things, but defining very complex things that were the basis of actual mathematics as it was done by professionals. The creation of bigger and bigger libraries, and in particular here I'm talking about Lean, so their MathLib library. And most impressive of all, Lean was used to verify new work by a very eminent mathematician, work that he was actually worried about its correctness. This was a truly great achievement because suddenly we are seeing a proof assistant dealing with research level mathematics of the freshest possible and the most sophisticated possible. The point of this, and this phenomenon was pushed largely by Kevin Buzzard, to handle complexity. So his complaint was that the prior achievements that I mentioned were typically long proofs about simple things, whereas mathematics today is often involving very sophisticated things. Now I would like to tell you about my own project, which I got a lot of money for from the ERC. Thank you to them. Its aim was to support working mathematicians, to build tools and libraries, and to answer the scientific question, what can we do with the tools we have today? What kind of mathematics can we formalize? What kinds of proofs can we formalize? And incidentally, not using Lean, but using Isabelle Hall, because it's a lot better. What did we look at? Well, the project has finished now, so I can very quickly list the things that we did, and there are lots of them here. I won't read them out to you. A lot of this is very sophisticated work, some very complicated and lengthy proofs here. Ordinal partition theory. This is a very abstruse subject that was pushed by Paul Erdős, so it genuinely counts as proper mathematics, but not, unfortunately, many mathematicians are not very interested in it. Grothendieck schemes. Now this Chemeretti's regularity lemma, which has something to do with very large graphs, is not as complex, not as difficult to prove as some of the others, but somehow much more impactful. And so in particular, this result on arithmetic progressions, which follows from it, and many other important results in mathematics, apparently. And then a bunch of things belonging to the field called additive combinatorics. So again, some very advanced, very modern mathematics, and also omega categories. So what we see here, first of all, we aim for a variety of different sorts of mathematics. We are also trying to formalize recent advanced mathematics rather than 19th century results. And the things highlighted in red were particular things that were thought to be difficult to formalize in Isabelle because Isabelle does not have dependent types. Isabelle is based on so-called simple type theory, and they were in fact not difficult to formalize. Now, what about that textbook? It's this Apostle, well-known textbook author, and this graduate text on number theory, covering lots and lots of things. I should mention the work that my colleagues and I have done so far, so notably Wenda Lee and Manuel Iberl, and I should also mention Anthony Borg, who helped set up this project. We did much more than I am presenting here. I am merely talking about the few things that I had something to do with. And I'm actually not going to cover the most difficult proofs because it's not really feasible here. The proofs I'm actually going to show you are on the whole fairly straightforward. Nevertheless, there are some interesting things we can see here. So here is a page from the book. Dirichlet's approximation theorem simply gives us a way of approximating any real number effectively by a rational number in a certain way. And you might say this is not very exciting, and indeed the proof is quite elementary. Without studying the proof in detail, you can see that there's nothing particularly fancy going on here. In fact, this theorem is basically proved by the pigeonhole principle, where you make these n+1 different real numbers and show that these n+1 numbers, two of them must fall within a single interval of which you have only n, and that proves the theorem. So that's nice and easy. Now, among the problems that came up here was Apostle overlooked that he would need a simultaneous version of this theorem. That is, a version that allows us to simultaneously approximate n different real numbers. I was able to find this proof elsewhere, and it's still not too difficult. You just have to kind of push it to n dimensions, and we can almost get the proof on a single slide. So here is the proof. Now you can see where I have hidden 35 lines. It's a very nice feature of Isabelle's user interface that you can hide subsections of a proof according to its hierarchical structure so that we can see this proof at this higher level. The point I want to make, of course, you are not going to be able to read this code, but maybe you can pick out little bits and you can see that there is something to be read in this code compared with if you've ever looked at a Coq or a Lean proof script, where they really give you an incomprehensible list of commands. Here you can see at the beginning we fix our variable theta. We have n greater than 0. You can read the conclusion there, relatively straightforward mathematics. Further on down, we define certain functions, and then you can see we are stating and proving a variety of intermediate results until finally we reach our conclusion. So that's an example of a simple theorem and a relatively straightforward formal proof. The chapter continues with various complex things, a few of which we are going to see here. So I will eventually get us on to here. The thing I'm going to show you next is actually one of the applications. So this theorem, we are talking here about periodic functions on the complex plane. So f, which maps the complex plane into itself. It's periodic if there is some omega such that every time you add omega to the argument, you get the same result. And if it has three separate periods, omega 1, 2, and 3. That's what this particular theorem is about, and it's saying that if it has 3 periods which are independent in a certain way, then it has arbitrarily small periods which effectively will tell you that it is going to be a constant function, except in assuming it's continuous or something. Okay, now again, the proof is relatively straightforward. Now again, you don't need to read it in detail, but you can see there's a case analysis. A certain fraction is real, or it might be rational even, or not rational, or not real, and then there are further cases, A, B, and C, blah, blah, blah. So this looks like a straightforward proof. But he goofed. So Apostle, in proving his theorem and going through all these cases, had in mind to use an approximation theorem called the Kronecker approximation theorem. But he did it wrong. So he did a lot of stuff trying to set up the preconditions for Kronecker's theorem. But in fact, it failed. Now, I don't want to go into the details. It's a rather subtle point. But in fact, Kronecker's theorem is not applicable here. And in fact, he doesn't need, it's actually quite a strong theorem, and he did not need its strong conclusions either. What he needed was Dirichlet's theorem. And if this was a moment when I had to go and dig up a proof of Dirichlet's simultaneous theorem and prove it, as I've shown you the proof already. Now let's look a bit at the formalization of Apostle's argument, a bit of it. So here again I've hidden things, and here again the main point is simply for you to see that when you look at this code, there is something that really looks like mathematics. You can read the claim at the top. You see F maps complex to complex. There are these 3 complex numbers. They are all, F is periodic in all 3. They are independent, they are distinct, blah, blah, blah. We've got epsilon greater than 0, and etc. Further down, you can see some of the case analyses. So we see whether this certain ratio is a real number or not, and so on and so forth. So here, so as I explain you right here, the first case, when this ratio is real, and if it is not real, then it turns out you can express omega 3 in terms of omega 1 and omega 2. Then you have further case analyses on whether alpha and beta are rational numbers. And finally, final cases when they are both irrational, and then we have to use Dirichlet's approximation theorem and do a big calculation. And there it is. So once again, the point is merely to show you what a reasonably legible proof looks like. So if you learned a little bit of Isabelle, you would be able to read some of this. So here we're defining a thing called theta, defining a quantity called delta. In fact, you can see delta is epsilon over a certain number. We show that delta is greater than 0, and on and on and on. And the reason I keep stressing this is because I think a formal proof needs to be understandable in its own right, even when you don't have a computer with you to check it for you. Now for another example. So Apostle came up with an application to the Riemann zeta function. Now I'm not going to mention what that is, but if you Google it or if you look and search in YouTube, you will find oodles of videos telling you what the Riemann zeta function is. Anyway, his example is to find the infimum and supremum of this quantity, where zeta, of course, is the zeta function, applied to a complex number of the form sigma plus I theta, sigma plus it, where the real number sigma is held constant. So there was a mistake in the proof, and that's what we always find when we formalize mathematics. We find mistakes, but we also find things that are tricky. So in this particular example, the problem is that he writes S, and when he writes S, he means sigma plus IT. And you are meant to know that S equals sigma plus IT, because he never actually says it. Apparently it's a convention used in this field, but it's a convention, but sometimes it's not actually holding, and sometimes S is simply S, and it makes it completely ambiguous when you see the letter S. What is he talking about? Or when you see T, does it relate to S or doesn't it? Well, it's hard to be sure, and this, I think, led Apostle into lots of problems. So here is another page, and again, this material is not particularly difficult, but let me show you something. So the problem here, he's talking about something being very nearly an equality for certain values of t, and then you scratch your head and say, where is t? Well, but eventually you find out, as I told you in the previous slide, that S equals sigma plus IT. So t is not mentioned explicitly, but you need to know that he's actually talking about that. But later on, he gets into difficulties over exactly this sort of thing. Now, I just want to show you how the proof begins. So, lots of things going on here. This is merely setting up what is a very long proof. So we create an enumeration of the prime numbers, and we show various facts about it. And there is much more work to do that comes after this. So the tricky thing, because the whole point of this proof is to calculate a certain value of t that is required to achieve the result that he wants. But there is the circularity, which I hinted at. Unfortunately, the details of this are too complicated to give in this particular talk. Just want to say that the proof that he gave did have a circularity, and I had to go on Math Overflow and get some tips from a very helpful person to find a way of constructing this T without the circularity. And what we see here is the examples that show you the ideas, show you the concepts, show you how they are used, but the proofs don't quite work, which is very commonly the case. Now, that was a little bit from chapter 7. In fact, I skipped all the hard stuff there, but never mind. Let's go to chapter 1, where he have 3 trivial proofs. Now, never mind what an elliptic function is or what a period parallelogram is. That is not the point. The point is that this has a one-line proof, but not when we formalize it. Again, a one-line proof. And by the way, whenever anyone says the edges cancel out, you're screwed, because that kind of informal talk turns out is very unlikely to work when you formalize. Here we are again. Once more, it doesn't matter exactly what the theorem is about. If the proof is one line, it should not take 200 lines to formalize. So again, we see he's conveying the ideas. That is, the idea of the proof is you use Cauchy's theorem to do blah, 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 but clearly there's a huge amount of detail that he's not bothered to tell us about. Now, some remarks about the project as a whole. My colleagues and I did 4 chapters. We would like to do more. Much of the material is straightforward. There is some tricky stuff, but even the tricky stuff went through okay. but there were a lot of mistakes, and also there are a lot of big gaps. Now, I've been handicapped here because, unfortunately, I never had a course on complex analysis, so this made it all rather tough for me. If you're going to formalize mathematics, it really helps if you understand the material you're formalizing.